The last topic for this unit is looking at the different properties of ionic and molecular compounds. Now that we know a little bit more about ionic and molecular compounds and what wakes them up, we're going to look at the properties of them, and the big key thing about this video is that we need to explain why we see those properties. So the first property that we're going to look at is melting points and boiling points. So hopefully you know what a melting point and a boiling point is at this point, but just in case, we'll go over the straight definitions. So the melting point is the temperature at which a compound changes from a solid to a liquid. And for water, hopefully you remember that's at 0 degrees Celsius. The boiling point is the temperature at which a compound changes from a liquid up to a gas. And so for water, that happens at 100 degrees Celsius. Okay. This is going to become a little bit more important as we go through. So for our next slide, we're going to look at the melting and boiling points of ionic compounds. So ionic compounds are made up of cations and anions. So remember that your cations are your positively charged ions and your anions are negative. And they're locked into a regular structure called crystal lattice. That's a new word for you, and you need to make sure you remember that, crystal lattice. Ionic bonds are very strong and are very difficult to break. And although ions are charged, overall the ionic compounds are neutral. So remember when we were doing our naming and I used to tell you to check your charges and crisscross? That's to make sure that the overall ionic compound is neutral. Which means your cations and your anions always combine in fixed proportions so that the sum of the electrical charges is 0. And an easy example is sodium and chlorine, and they combine in a 1-to-1 ratio, making the formula unit for sodium chloride Na1. Cl1, or just we write NaCl. So we talked quickly about this crystal lattice. I want to show you a picture of what this sort of looks like. So here are two examples. So the first one is sodium chloride, and the second one is calcium fluoride. So you can see sort of a really regular cube structure here, and you can see you've got the small sodium ions, the bigger chloride ions, but they all kind of intertwine and bond with each other. So it's not just one sodium and one chlorine bonding together. They make up this big, huge crystal, and there's billions of molecules or atoms that bind together to make these crystals. And that's why when you look at salt, like table salt, you actually see regular shaped crystals. Calcium fluoride, same thing. The only thing is you have to have 2 of these green fluorides for every 1 calcium. So the structure of it doesn't end up being a cube shape. It ends up looking a little bit funny. Now I will never ask you to draw these, but I just wanted to show you these pictures so you understood what exactly a crystal lattice was. In order to go from a solid to a liquid or from a liquid to a gas, we basically have to break all these blue bonds here. Okay, so you can see that because there are so many, because ionic compounds form this crystal lattice, it makes it really, really difficult for an ionic solid to go into a liquid or into a gas form. So that means it takes a lot of energy to melt or boil these substances, which means that their melting and boiling points are very, very high. All right, next up are molecular compounds. So these guys have lower melting points than their ionic compounds. Those with non-polar bonds will have a lower boiling point than those with polar bonds. So remember we talked about what happens if a molecule is polar. That means it has partial charges. So if it has a partial charge, even though those charges are not full-on charges like in ionic compounds, they can still attract, and that kind of holds these molecules together like a magnet, and it gives them a higher melting and boiling point. If you look, I don't have an example on here, but if the molecule is non-polar, then there are no partial charges holding anything together, and therefore the melting points and boiling points are lower. So it makes it really easy to go from a solid to a liquid because there's not a lot of forces in between those molecules. So these partial charges we're going to look at a little bit later, and these sort of attractions in between the molecules, these are a type of intermolecular forces called a dipole-dipole force. If you want to write that in now, you can, but if not, it will come up later in one of the other slides. So, holding it together. If we look at this, consider a glass of water. Why is that? There we go. If we look at a glass of water, why do the molecules of water stay together? Basically, there must be attractive forces that hold them together. So, let's look at the different types of forces that there are. Intramolecular forces occur between atoms, and those are the bonds, okay? That's what we've been studying up to now. So the bond between a hydrogen and an oxygen there and there, those are intramolecular forces. They're within an atom. Intermolecular forces, you can see my little arrow pointing to those, are the forces that are in between the molecules. In order for this to happen, we have to have a polar molecule or a dipole. We don't consider intermolecular forces in ionic bonding because there are no molecules in ionic bonding. Again, it makes that crystal lattice structure, so there's no official molecules. All of the ions just kind of bond to each other. This type of intramolecular bond will determine the type of intermolecular force. So if you have a very polar covalent bond, you're going to have a different type of intermolecular force. So that's what we're going to look at next. So you guys need to know from this slide the difference between an intramolecular force and an intermolecular force, okay? All right, next up is this dipole-dipole force. So like I said before, the dipole-dipole force happens when you have a polar molecule. So your electronegativity differences between covalently bonded atoms in a molecule result in a bond dipole. So when your electronegativity is between 0.4 and 1.7, you can have a polar bond, and therefore you can have these dipole-dipole forces. So it's an attraction between oppositely charged ends of polar molecules. So for example, if each one of these gray circles is a different molecule, I'm going to draw in the dipole-dipole force, okay? So in blue, here's my dipole-dipole force between those molecules. It would be here and here and here and between those ones. So you can see you can still form quite a few dipole-dipole forces in these polar molecules, okay? As the polarity of the molecules increases, so will the dipole-dipole force. So if you look at fluorine and bromine compared to fluorine and chlorine, your fluorine and bromine bond will be more electronegative than the fluorine and chlorine bond. So if you actually do your differences in electronegativity using the electronegativity values on the periodic table, you'll see that the difference between F and Br is greater than the difference between F and Cl. So that means if I were to compare these two compounds, the FBr has a stronger dipole because it has a bigger difference in electronegativity. And if it has a stronger dipole, that means it's got a much higher melting point, MP, or boiling point, BP. All right, so the relative strength. So remember, the relative strengths of the different intermolecular forces relate directly to the melting and the boiling points. So if you have strong intermolecular forces, you have a higher melting and boiling point. If you have weaker intermolecular forces, you have a lower melting and boiling point. All right, so solubility in water is another trend or another property of ionic and covalent compounds that we have to look at. How does something dissolve in water? Basically what has to happen is the forces between the water and the particles must be stronger than the forces between the water molecules alone. So I have a little animation here. I'm not sure if it's going to work when I click on it. It doesn't look like it's going. All right, let's see if I can get this. There we go. So here is what happens when I dissolve some sugar in water. So take a quick look at this. This is a little bit cheesy, so watch out. Okay, so here are my sugar molecules. What happens is the sugar molecule is polar and is attracted to the polar ends on the water molecule. So if enough waters go around each sugar molecule, they will actually rip apart that sugar cube and the sugar can dissolve in water. So basically the forces between the water molecules and the sugar molecules have to overcome the intermolecular forces between all the sugar molecules that were initially present. So that is why some covalent compounds that are polar can dissolve in water. So if you look down here, not all ionic and polar compounds are soluble in water, and we look at this in a lot more detail in Unit 4. All right, last property is electrical conductivity. So some substances will conduct electricity when dissolved in water. So why is that? In order to conduct electricity, if you remember from grade 9, electricity means, or sort of the definition, or I guess, is moving electrons. So in order for electricity to happen, electrons have to move. So they have to be free to move, which means we have to have ions that are dissolved in water. So ionic compounds can conduct electricity when they're dissolved in water, because then the electrons are free to move. They can also, as a side note, conduct electricity if they are molten. So if they're in the liquid form, they can also just conduct electricity. Molecular compounds, however, have no charges. Therefore, the electrons are not free to move. Then you will see no conduction of electricity. All right, that's it for this video. Here are some key terms that we looked at that you need to know. Whoops, I don't know why that writing is there. That you need to know for this video. If you have any questions, we'll take them up in class.